So next is the Möbius inversion formula. I will introduce you to another naturally defined function on a positive integers, which is the Möbius mu function. So let's define the Möbius mu function. For a positive integer n, define mu by the rules mu n is equals to 1 if n is equals to 1, 0 if p squared divided by n for some prime p, negative 1 to the power of r if n is equals to p sub 1 times p sub 2 until p sub r, where p sub I are distinct primes. To put somewhat differently, it states that mu n is equals to 0 if n is not a square-free integer, whereas mu n is equals to negative 1 to the power of r if n is square-free with r prime factors. For example, mu 30 is equals to mu times 2 times 3 times 5 is equals to negative 1 to the power of 3 is equals to negative 1. The first few values of mu are mu 1 is equals to 1, mu 2 is equals to negative 1, mu 3 is equals to negative 1, mu 4 is equals to 0, mu 5 is equals to negative 1, mu 6 is equals to 1, and so on. If p is a prime number, it is clear that mu p is equals to negative 1. In addition, mu p to the power of k is equals to 0 for k is greater than or equal to 2. So, as you may have guessed already, the Möbius mu function is multiplicative, and this is the content of theorem 6.5. So the theorem 6.5 is the function mu is multiplicative function. So the proof is we want to show that mu m times n is equals to mu m times mu n. Whenever m and n are relatively prime, if either p2 l times n or p2 l times n. So p a prime, then p2 l times m times n. Hence, mu m times n is equals to 0 is equals to mu m times mu n. And the formula holds trivially. Then, we therefore may assume that both m and n are square-free integers. Say m is equals to p1 times p2 until p7. Then n is equals to qi times q2 until qs, with all the primes pi and qj being distinct. Then mu m times n is equals to mu p sub 1 until p sub r times q sub 1 until p sub s is equals to negative 1 to the power of r plus s, and it is also equals to negative 1 to the power of r times negative 1 to the power of s equals mu m times mu n, which completes the proof. So next slide is, let us see what happens if mu d is evaluated for all the positive divisors d of an integer n and the results are added. So in the case where n is equals 1, the answer is easy. So here is the example. Summation of d divided by 1, mu d is equals to mu 1 is equals to 1. Suppose that n is greater than 1 and put f of n is equals to summation of d divided by n mu d. So to prepare the ground, we first calculate f of n for the power of a prime. Let's say n is equals to p to the power of k. So the positive divisors of p to the power of k are just the k plus 1 integers, the 1, p to the power of 2, until p to the power of k, so that f of p to the power of k is equals to summation of d divided by k to the power of n mu d is equals to mu1 plus mu p plus mu p to the power of 2 plus until mu p to the power of k is equals to mu1 plus mu p is equals to 1 plus negative 1 equals 0. So because mu is known to be a multiplicative function, an appeal to theorem 6.4 is legitimate. This result guarantees that f also is multiplicative. Thus, if the canonical factorization of n is n equals p sub 1 to the power of k sub 1 times p sub 2 to the power of k sub 2 until p sub r to the power of k sub r, then f of n is the product of the values assigned to f for the prime powers in this representation. So f of n is equals to f of p sub 1 to the power of k sub 1 times f of p sub 2 to the power of k sub 2 until f of p sub r to the power of k sub r is equals to 0. So we record this result as theorem 6.6. So the theorem 6.6 is for each positive integer n is greater than or equal to 1. So summation of d divided by n, mu d is equals to 1 if n is equals to 1 and 0 if n is greater than 1, where d runs through the positive divisors of n. For an illustration of this last theorem, consider n is equals to 10. The positive divisors of 10 are 1, 2, 5, 10, and the desired sum is summation of d divided by 10, mu d is equals to mu1 plus mu2 plus mu5 plus mu10 is equals to 1 plus negative 1 plus negative 1 plus 1 equals 0. So the full significance of the Mobius u or mu function should became apparent with the next theorem. So the next theorem will be discussed by the next reporter.